So we take a look at sodium chloride. Please, yes. We add that to water, we'll end up with Na plus and Cl minus. So you could look at that and say, oh, that's a reaction. If we did the same thing with our sugar, anybody know the formula for sugar? Dang it. Can't just make it up. C6H6O6? That's what I get. Should have just said something else and it wouldn't have mattered. What do we get? We get C6H6O12. Did a reaction occur? No. So when we look at the reactions, we go, oh, okay, sodium chloride is very clearly a reaction. Okay, something happened. It did change its properties. Sugar did not. We get the exact same thing on both sides of the equation. So when we look at a reaction equation, that can help us decide if we actually had a reaction or not, okay, in some cases. So what is a reaction equation? So now that we've got our reaction, or a generic form of our reaction, drawn out, we can go through and start to identify important aspects of it. What are those important aspects? We can look at our phases. So our phase for each of our species is specified in parentheses after the species. So we've got gases for G, we've got liquids for L, we have solids for S, and then we have aqueous, meaning that compound is dissolved in water. So by writing aqueous, we're actually saying two things. We're saying not only is there compound D, but there's also water. Okay? So just by writing AQ, that actually implies the presence of water. So in our reaction, if we were to try and describe what was present, we could say A was there, B was there, C was there, D was there, and H2O. Okay? Because that's what that AQ is signifying. Okay? What else does our reaction equation give us? Specifies that a reaction worked. Okay? So what we've got is reactants on one side, and on the other side we have products. So what ends up happening is our arrow in between is representing that something has occurred, that we've now changed around our A and B to go through and make something on the other side. Okay, so we've got a bunch of information stashed in our reaction equations, and we'll keep revealing more information as we go, because as we, of course, go through, we try and start simple. And the internet died again. We try and start simple and go from there. Hopefully it'll reconnect here in a second. Wow. Now the computer's frozen. So your textbook lists off a bunch of different things that can be specified within the reaction equation. So what you would look for and what it means. You're responsible for recognizing those. The primary ones that we just talked about, we're looking at the reaction equation. It's going to work. Okay, our reaction arrow, and then our phases. Some of those other symbols you may need to recognize. For instance, the plus sign means we just added two things together, or there's two things present. So it's a way to separate our reactants from each other. It's a way to separate our products from each other. So we don't put all the symbols smashed up against each other, so that way we know they're different things. Okay. The next sequence of arrows, probably not as important. Okay. The more chemistry you take, the more likely you'll run into those. NR is just a nice simple abbreviation for no reaction. So depending on where you write that, or at what point you want to specify that there's no reaction, you may see that show up in a variety of spaces. The one with the delta symbol over the top, what did delta mean? Change. In this case, the delta symbol is referring to a change in temperature. Okay, so we're looking at an addition of heat to the reaction. The one with the Fe over the top of it, okay, that Fe could be anything. Okay, they're just using Fe as an example here. What we're saying is over the arrow, that would be a catalyst, something we've added to the reaction to help it work. Right? For the sake of general chemistry, it's probably true. If you move through, you'll notice, or move through other chemistries, we'll start to change where things show up within certain limitations. Right? So be aware this is not going to hold true for all chemistry. Okay, that wasn't supposed to happen that way, but it worked. So let's take a look at a chemical reaction. What can you tell me about this chemical reaction? So we're taking a solid and we mix it with a solution. Okay, what happens when that occurs? We get a gas and leftovers of our solution. Okay, so we looked at the phases. What else could we look at?
Sodium nitrate attached to the other.
So you brought in a couple things here by referring to the sodium hydride and then attaching to the other. That other one, of course, is more difficult to name. What's the name of that other one? Acetic acid. So our sodium hydride broke, okay, and reacted with the acetic acid to generate some new products. So one thing we could go through and do is start to bring names into this. So when we talked about nomenclature and how you have to go through and name everything, guess what? You can't forget it. It's going to show up again. Okay, so you have to be able to go through and apply. Okay? Where I think you were then alluding to after that is what was the result of the reaction? What happened to the sodium? It became part of the other species. What happened to the hydride? It separated and became part of a gas. So what we're looking at across the reaction is what things changed. Okay, that's the primary thing that you should be getting out of any kind of chemical reaction. What things changed in the process of going through that? Okay. That concept gets exceedingly more difficult as you move through chemistry. But it's ultimately the same idea. What things changed? If you can identify what changed, you can then start to make some conclusions about the overall reaction and potentially the feasibility of the reaction. Okay. Next part that we kind of want to get into is something that I forgot to talk about when we were looking at nomenclature. What's the name of that species that's boxed in? It's kind of a tricky one. What type of bond do we have?
It's not a bond.
If there's two elements, is there a bond? Because if we're saying there's not a bond, then we have two hydrogens offloading by themselves and they aren't connected. Well, if they aren't connected, would I write it as H2? No. So there is definitely a bond there. It's a nonpolar covalent bond. And if we go think back to our rules of nonpolar covalent bonds, how might we name this? I know it's kind of a tricky one. Switch it up to HCl. Is that one going to show up on that screen? Let me go underneath. So we've got a different example for a nonpolar covalent bond, or sorry, a covalent bond. How do we name this one? What was that? A couple people said it. The first species is hydrogen, and we leave its name alone. We just call it hydrogen, and the next species is chloride. So we name the first species as its standard name, and we name the second species as the "ide" ending. So let's go back up to our H2. Not quite just hydride, it would be dihydrogen, or take it a step further, if this is breaking down exactly as we looked at the nonpolar covalent bond, we're looking at hydrogen hydride. That's really weird. And that implies that the hydrogen is different. The hydrogen on the left is different than the hydrogen on the right. Well, in the case of HCl, is that very clearly true? Is hydrogen definitely different than the chloride? Yes. Why are they different? What's one of the primary differences between them? I can come up with all sorts of answers for this. That's the lovely answer that I wanted to hear. Electronegativity. Okay. Chloride is more electronegative than the hydrogen, meaning that the chloride builds what charge? Partially negative, because it's now accepted those electrons, taken some of the electrons away from the hydrogen. Okay. What happens when we go up to the HH bond? It's the exact same element. There's an equal pole. Okay, so this structure starts to become really weird, and it doesn't quite match the nomenclature system that we've been working with. Okay? We'll notice that there are seven total elements that all fall under this category. Okay? And because the name would be kind of weird if we named it as hydrogen hydride or even dihydrogen, what we do is simplify it all the way down and refer to it in its elemental state as hydrogen. Okay? No hydrogen ion, no hydride, it's just hydrogen. And when we write out the formula for just hydrogen, the formula necessarily implies that there are two hydrogens present. Okay? So our formula for hydrogen gas is H2. What if I asked you for the formula for, that's a lot of erasing, chlorine gas? Okay. Could be tricky if we weren't looking perhaps at the figure. What's our symbol for chlorine? Cl. We just said hydrogen was one of these weird tricky elements. And if we look at that weird periodic table, what do we have? You see there's a nice little bubble pointing at hydrogen showing two elements. Where's chlorine on this table? Yes, it's on the right. It also has weird little arrow pointing to a blow-up of two elements. Guess what happens when we look at chlorine gas? It's Cl2 as well. What if I looked at sulfur gas? Okay. Does sulfur have a neat little arrow pointing to it, showing a blow-up of those pictures? No, it doesn't. Sulfur is just going to be written as sulfur, specifying our phase, sulfur gas. Okay, so go ahead.
Well, naturally they're already in gases. Why did they be H2 or CO2?
So what we're saying is that the element on its own is not stable, and it has to interact with a like molecule or some molecule. So when we look at hydrogen, it's found pretty much everywhere. Okay? In this case, if we're going to look at hydrogen on its own, we just take a bunch of elements, single atoms of hydrogen. They're so unstable that they will have to interact with another atom. Okay. So they will react with each other to form this H2 molecule. How do we know which elements are going to form this diatomic species? Because I told you, or the fancier answer would be, you had to have it memorized. Right? So you will have to have it memorized as to what elements are diatomic. Okay, so there are 7 of them, as we alluded to. Hydrogen, nitrogen, oxygen, iodine, chlorine, bromine. Did I already say iodine? Oh, I did. I meant to say fluorine. Okay? So those 7 elements are diatomic. Might be nice if we had some kind of device to go through and remember those 7 elements. Any ideas?
What makes number 7?
Okay. If we take a look at the nitrogen and go across, we've got 7, right, on our periodic table. So we draw that up on the screen. We have the number 7 right there. We'd have to remember the hydrogen is a floating point, but that works. Okay, so that's a common one. There's another one that maybe a few of you heard that I mentioned in lab. Remember that one? Have no fear of ice-cold beer. Okay? Have represents hydrogen, no, nitrogen, fear, fluorine, of, oxygen, ice, iodine, cold, chlorine, beer, bromine. Does it work perfectly? No. It gets you pretty close. For instance, the symbol for chlorine is not CO, it's CL. Okay? But it gets us at least within a ballpark that if we see one of these elements, hopefully remember that goofy little name and know that, oh, that's got to be diatomic. How do we know we'd be looking specifically at a chlorine atom and not chlorine in its diatomic state? There's a hint, I just said it. I want to look at chlorine atom, what do I need to say? I'm looking at chlorine atom. If I'm looking at the diatomic molecule of chlorine, we immediately say it's chlorine. And it's assumed that we have to have two chlorines. If I only want to look at one, I have to say I am only looking at one. And I can say that by saying chlorine atom, because the atom implies a single value, because it's not plural. Okay? So those are our diatomic molecules. We need to be aware of those when we go through and deal with our reactions, particularly when trying to name these things. Okay? The next fun part about this, or at least this section of material, is we're now going to bring numbers back into the game. So when we write out a chemical equation, we have to follow the laws of, depending on how you want to look at it, physics or chemistry. Okay? And if we think all the way back to our first or second chapter, we said we had the law of conservation of mass and energy, which meant what? I cannot create or destroy mass or energy. Okay? Which means if I start with a mass of sodium here, what has to happen on the other side? I have to have the equal mass. Okay? Because we can't create or destroy these things, at least at this stage, okay, we need to make sure that they balance across the reaction. So if I look at the left side of the reaction, how many sodium atoms do I have? 1. If I look at the right side, how many do I have? 1. Did I create or destroy sodium? No. So my sodium's fine. How about the hydrogen? It's a little bit trickier. So if we write this out, our sodium, we said 1 on the reactant side and 1 on the product side. We now shifted to our hydrogen. How many hydrogens do we have on the reactant side? Why 5? I only see 1 right there next to sodium. We have to add all of them. We aren't now looking at the individual molecules. We're looking at the total atoms on the left, the total atoms on the right. So how many hydrogens on the left? We've got, where's my letter? 5. How many on the right-hand side of the reaction? 5. I also have 5. Huh, that's kind of nice. What about carbon? 2 and 2. I didn't check the hydrogen. Yeah, okay, that was good. Oxygen? 2 and 2. Our reaction now actually gives us more information. Okay, because our reaction is now balanced. What is that more information that it now gives you? It's finished. Okay, we don't have to worry about balancing it anymore. If I take 1 molecule of sodium hydride, how many molecules of acetic acid do I need to react with it? 1. How do I know that? Okay. Then let's switch it up. Let's say 2 molecules of sodium hydride. I don't see a 2 in here. So if I give you 2 molecules of sodium hydride, how many molecules of acetic acid do you need to react in this fashion? 2. 2. Why 2?
1 to react with 1 and 1 to react with the other.
1 to react with 1 and 1 to react with the other. Okay. What if I give you 6.022 times 10 to the 23rd molecules? Come on, you can regurgitate that number out. How many molecules of the sodium acetate do we need? Oh, good job with memorizing that number. That number will become particularly important later in the semester. Okay, so our equation is getting us a relationship between the numbers of these things. Okay? If we want to now convert that thought process into a mathematical equation, okay, can we do it? Let's write it out. I asked, starting with 1 mole of sodium hydride. Let's try that again. You don't know what a mole is. 1 molecule of sodium hydride. And what did I want for an answer? The molecule of our acetic acid. Okay, we think back to the beginning of the semester. We looked at these conversions. Oh my gosh, it's an equation. We need to be able to do a conversion to get across. Okay, in that conversion, what needs to disappear from my final answer? Someone said it. The sodium hydride needs to disappear. I don't want sodium hydride, so I'm going to put molecules or molecule of sodium hydride down here. So now that unit can cancel. What unit do I want at the end? Molecule of our acetic acid, right? The HC2H3O2. That's my target answer. What is the conversion factor between those two values? How do you know it's 1 to 1?
Because the equation balances with one of each.
We look at the coefficients from our equation. What number did we write in there? There's an implied 1. Why is it not 0? I didn't write a number.
There wouldn't be any reaction at all because you have nothing.
If it was a 0, I'm saying that element's not there. So when we look at our reaction, we could go through and put zeros in for everything that's not present. But think about all the chemical molecules out there in the world. Do we really want to go through for every single equation write in everything that's not present? That's a lot of work. So we have an automatic implied 1. So when I switch this up to 2 molecules of sodium hydride, what happened? We changed the number in front. What did we do to our conversion factor? Stays the same. Our conversion factor will always stay the same from whatever we're trying to relate to. Does that mean all reactions are going to be 1 to 1?
No.
No. So our balanced equation allows us to convert from one species to another species. Incredibly difficult to do without a balanced equation. We have to have some way to relate those species. That's what our equation does. Okay? So, we've got a balance all the way through to deal with this. Our coefficient is going to multiply everything that happens after it. So if, for instance, I wrote 3H2O, how many hydrogens would be present? 6, because that 3 applies to the hydrogen, but there's already 2 hydrogens present, so I get 3 times 2 and 6. All right, let's try it with a different example. Let's make it a little more challenging. Let's look at our acetic acid again. Nice big old box. How many hydrogens are represented in that box? Our formula tells us there's how many hydrogens? 4. How many of those formulas do we have? 3. So we could add 4 plus 4 plus 4, and we get 12, or 3 times 4. How many oxygens? 6. Our formula tells us there are 2 oxygens, as seen from the 2 that refers to our oxygen. And then this 3 applies to everything afterwards. Okay, so our subscripts only refer to the element directly in front. Our coefficient, the number in front, refers to everything after it up to some kind of symbol. Okay? Be it our reaction arrow or saying we've switched to a new species. Okay? So, guidelines for balancing reactions. Okay, and one of the first things that we'll look at in a little bit here is you need to predict the products if necessary. Okay, so sometimes I'll just give you the reactants and say, hey, tell me what happens. You need to know how to predict those. There's certain equations you're expected to do, some you're not. Okay, so if you've got to predict the products, then you'll go through and balance your formulas. You've got to make sure your formulas are correct. How do you know the formulas are correct? If our overall charge for the formula comes out to be 0. So if we look back at our example, is sodium acetate a balanced formula? Okay, I see you nodding. Why? How do you know it's a balanced formula? What is the charge on sodium? What is the charge on acetate? How many acetates are present? How many sodiums are present? What happens? Our overall charge equals 0. Is our formula balanced? Yes. Okay. This should also be kicking back alarm bells to thinking, oh crap, we did this in nomenclature. Yeah, guess what? You need to do it again and again and again. You cannot forget how to balance your formulas. Okay? If you don't balance the formula properly, you can't balance the equation. Okay? So if you needed more practice with it, guess what? You get more practice. Yeah?
I think I missed something. How come you just put the +1, -1 over the name and not over the C?
Okay, so that breaks it down to the name of this compound. What is the name of this compound? Sodium for the Na. What's the name for C2H3O2? How do we know it's acetate? You've had it memorized. It's one of those complex ions that you have to have memorized. With that, when we go through and go from the name to our formula or our formula to the name, we have to know something about our charges. Because what type of bond do we have between the sodium and the acetate? It's an ionic bond. Okay? Is it binary ionic or ternary ionic? Ternary. So we would have to go through and say, okay, what is the charge on the sodium? How do you know it's +1? You had it memorized. Okay. What was the charge on the acetate ion? -1. How did you know it was -1? Unfortunately, you had it memorized. Okay. How many sodiums are there? How do you know there's only one? We look at our formula, because we're testing our formula to see if it's correct. Okay. It doesn't have a subscript, so we're looking at a 1. How many acetates are present? Why is it not 2? The 2 is as much a part of the name of acetate or the formula of acetate as the N, or the A is part of the name or formula for sodium. Okay, so when we're looking at our acetate, what we're really saying is parentheses, what is this number? Which conveniently circled 1. When we go through and do that math, we verify that our formula is actually correct. What if our formula was incorrect? Start over and fix it. Okay? Once you've done that with all of your formulas, then, and only then, can you start to balance the equation. Okay? General rules for balancing the equation. Okay? Balance any atom that you really want except for hydrogen and oxygen. It's just kind of a general rule of thumb. It becomes more relevant when you deal with more advanced equations. Okay? You will place whole numbers in front of the formula. So now what we're going to do is change the coefficient. Okay? We cannot touch the formulas anymore. So no more subscripts. We've got to put a number in front of the whole formula. Okay? To increase the amount of that particular atom so that it balances on both sides of the equation. We then, step 5. We'll go through and repeat step 3 and 4 until we've checked all of the atoms. Okay? And this is where most students stop. Oh, I checked all of the atoms, so I must be correct. Okay? Do not stop. That is not the end. What do? Check your work. Now you get to do the whole problem again, starting with the very first element, and check how many atoms it has on the reactant and how many atoms it has on the product side. Okay? What if it still doesn't balance? Well, in the process of repeating step 3, you have to change numbers. Well, as soon as you change numbers, you'll go through steps 3 through 5 again. You go, oh, well, I balanced it a second time, so it must be correct. No. Do step 6 again. Check your work. Start over again. The moment that you have not changed any numbers is when you check 3 more times. If after 4 checks the numbers have not changed, then you're good to say you got the correct answer and you're happy. Okay? Very last thing that you can go through and do is verify that you have the smallest whole numbers possible. It's again kind of a rare caveat, but it can pop up. Okay? So we got all the rules. You guys are perfect at it now, right? Really? Okay, so let's take a look at some practice. I'll go ahead and work through the first one, and then I'll make you guys deal with the last 3. Kind of mean, because the last 3 are more difficult than the first one, but might as well. So we take a look at that first one. To start our balancing, what do we start with? Start with atoms that are not hydrogen or oxygen first. So our first atom we're going to start with is, well, okay, crap. So we go back to rule 3. And now we can go through and start to balance our hydrogen or our oxygen. What do we want to balance first? Okay, let's take a look at the hydrogen. How many hydrogens do I have on the reactant side? 2. How many hydrogens do I have on the product side? 2. Awesome. First step done. Now we repeat with the next atom. What's our next atom? How many on the reactant side? 2. How many on the product side? 1. Is it balanced? No. What do we have to do?
Increase the number of atoms.
We'll have to increase the number of oxygens on which side of the equation? So our reagent side is the left side. If we increase the oxygens on that side, what happens to our tube? It gets bigger. That's not going to help us. So what we'll do is increase the number of oxygens on our product side. How do we do that? We will put in a coefficient 2 in front. Okay? What if instead I'd written it in a very bad method down here? Now I have 2 oxygens, right? Is the compound water anymore? No, we cannot change the compounds produced. Once we've predicted what they are, you cannot touch those formulas. So we have to put the 2 there. Now how many oxygens are on the right-hand side of the equation? 2. I said oxygen. So we go, cool, my hydrogen's balanced, my oxygen's balanced, now I'm done. That's the mistake that everybody makes. Okay? Step 6 was
Check your work.
go back and check your work. So we start with hydrogen. Reactant side, how many hydrogens do we have? 2. Nothing changed. Cool. Product side? 4. Are our hydrogens balanced? No. So what do we have to do?
Add 2 to hydrogen in the reactant.
We need to increase the hydrogens on the reactant side of the equation now. And we will do that by putting a 2 in front of our coefficient. The result? I now have 4 hydrogens on the reactant side. Does 4 equal 4? Yep. So now what do I do?
Repeat with oxygen.
Check with oxygen. How many oxygens on the reactant side? Oxygens on the product side. What do I do now?
Check.
Check it again. Hydrogen. How many hydrogens do we have? 4 and? How many oxygens? And? What do we do again? Hydrogen. How many hydrogens do we have?
4.
And?
4.
How many oxygens?
2.
And?
2.
What do we do now? Check it again. Okay. How many hydrogens do we have?
4.
How many hydrogens do we have? Oxygen. And 2. Is that extremely tedious and slow? Yes. And you're screaming at me, it's already balanced. Stop making me count. Okay. This is a simple example. In the simple examples, you can get to the balanced answer relatively quickly. That does not mean you shouldn't check. Okay? One last question that you might see pop up is, what is the sum of the coefficients of the balanced equation? Okay, and the reason why we would ask this question, coefficients, is that if you balance the equation properly, you'll get a certain number. Okay? That number is in our answer, and we don't have to check all of your work to go through and balance it. Okay? So, if we look at the coefficients, coefficient in front of hydrogen is 2, in front of oxygen, in front of H2O. That gives us a sum total of 5. The answer we get? 5. What other multiple choice answer would be there? 3. Probably see a 2. You'd probably see a 1. I'm hearing some 6s. I don't know why I hear a 6, but we'll go ahead and put it in there. Okay. Why? What's the coefficient in front of the oxygen? 1. There's an answer. What's the coefficient in front of H2? 2. There's an answer. Where'd the 3 come from?
Hydrogen and oxygen.
You didn't balance the equation, and you just added 1 plus 1 plus 1. Okay? All of the numbers in your answer choices are possible numbers that could be answers. Answer the question that's asked. If I ask you for the sum of the coefficients, it's all of them. If I ask you for the coefficient in front of oxygen, your answer is 1. Okay? So, give you some time to go through and work through. Go ahead and start. Second equation. We'll start with our hydrogen first. Actually, let's hold the pattern that we were talking about. Start with our bromine first. We said balance elements other than hydrogen or oxygen first. How many bromines on the reactant side?
2. Yeah.
We've got 2 coming from our formula. How many on the product side? 1. Is it balanced? What do? We need a coefficient 2 in front, so that now I have how many bromines? 2. Now I can move to the next element. What's the next element? Hydrogen. How many hydrogens on the reactant side? 2, because our subscript. On our product side, the 2 applies to everything after it, which means how many hydrogens are there? 2. Is our hydrogen balanced? Yes. What do? Check it. What do? Check it. What do? Check it. What do? Check it. Okay? For the sake of time, I'm not going to go through and check them all. Is it balanced? Beautiful. Next problem. A little bit trickier. Significantly trickier. Okay? Where are we going to start? Aluminum's not a bad place to start. Let's go ahead and start with that. How many aluminums on the product side? Or sorry, reactant side? 2. We look at the subscript that applies to the thing directly in front of it, and we have 2 aluminums. Move to the product side. We have 1. The 3 applies to the parentheses. Is the aluminum in the parentheses? No. So that 3 does not apply through. Is it balanced?
No.
What do you need to do? We need to put a 2 in front, so we're changing our coefficients. That now becomes 2. All right, are our aluminums now balanced? Yes. So now what we'll go through and do is I'm going to skip to barium. We'll talk about why in just a second. All right, how many bariums on the reactant side?
1.
Why did that 2 not apply to it? It's not in the parentheses, so it doesn't apply through. On the product side? 1. Is it balanced?
Yes.
Cool. Okay. So now what we're going to do is decide how we're going to balance that next sequence. Okay. What do you want to balance next?
I know.
Okay. I actually heard just 2 answers, which I'm actually surprised that I only heard those 2 answers. I heard SO4 and NO3. Is SO4 an element? Is NO3 an element? Why are you balancing things that are not elements?
It's easier.
It is much, much easier. Okay, but the only reason we can balance those larger units is because in the course of the reaction, what happened to the SO4? It stays SO4. So I do not have to break that up into the elements of sulfur and oxygen. If for some reason in the course of the reaction I do not see a unit of SO4 as a product, I have to balance the elements. Okay? For the sake of speed in this case, we'll go through and deal with our SO4. How many SO4s on the reactant side? How do you know it's 3? The 3 applies to the parentheses, everything within those parentheses. What is within the parentheses? SO4. We're trying to balance SO4, so there are 3 SO4s. Product side. Only 1. Are they balanced? What do you need to do? I need to have a 3, which means I put the 3 right here, right? No, that does what? Changes the formula. Once we start balancing the equation, you cannot change the formulas. So the 3 shows up in front. Are our sulfates now balanced? Yes. So what do we move to? We still have the nitrate, the NO3. How many NO3s are on the reactant side? 2. You know that because? Subscript and our parentheses. What's the other side? Product side.
3.
What was that answer? 6. Why are there 6 nitrates on the product side? We absolutely have that 3 applying through to the nitrate, but this 2 applies to everything that comes after it. So we have 6 nitrates. Is that balanced? What do we need to do? I need 3 of these, which means I end up with how many nitrates? 6. My nitrates are balanced. What do I do now? Check your work. Since I've got an eraser, let's go ahead and clean this up a little bit. All right, so we now look at all my work, and I go back to my aluminums. How many aluminums on the reactant side? Product side. Barium. But I wrote 1. Changed. So that's got to become 3. Product side. Ooh, wasn't that lucky. Is our barium balanced? Yeah. Sulfate. 3 and 3. Nitrate. 6. We've got the 3 and our 2 both multiplying our nitrates. Our nitrate on the product side. Same deal, 3 and the 2 multiplying our nitrates, we end up with 6. What do we do now? Check it. What do we do now? Check it. What do you do now? Check it. I'm getting kind of tired of saying that. What do you do now? Check it. Okay. Does it balance?
Yes.
Yes. So now we have our answer. We can go through, depending on what the question asks, we can then evaluate what we want to answer. Make sense? Okay. Take a look at the last one. Yes, no? It's already balanced. Okay, well, I want to add just a little bit more of a discussion on that. What is CO3? Yeah? Carbonate. Complex ion, just like sulfate and nitrate. Can I balance this reaction using carbonate?
No.
Why not? Carbonate does not show up on the product side. So when I go through to balance, I will look at carbon, oxygen, and hydrogen. I will not balance this based on the complex ion because the complex ion does not stay there. It changes in the course of the reaction. Okay? Yeah?
On the rules list, you said the hydrogen and oxygen come last after everything else. Why is that?
It's for a reason that we won't run into in this class.
And it doesn't
Kinda
matter
keep it
which
at
of
that
those two come first before each other?
No.
No.
Sort of. What you'll find is if you go through and follow the rules, you'll be able to balance the reaction. Okay? In certain cases, you'll find it's a lot easier if you balance one element versus another. how would you know which element to balance first? You don't. It's random luck of the draw, okay, at least at this stage. Until you pick up enough practice with balancing them to recognize the patterns and start to balance in your head, okay, it's a random luck of the draw what element you decide to pick and balance first. Oxygen and hydrogen typically can be very, very tricky, so we leave those to the very end. Okay?
Can you repeat the last one, please?
When we go through and balance, we leave oxygen and hydrogen to the very end. Those are going to be the last two elements we go through and balance. Okay? Any other element, doesn't matter what you start with, you will get to your answer. Some elements will allow you to balance the equation quicker or easier than others. Okay? And it's not based on the element, it's based on your reaction equation. Okay? So if you look at an individual problem and started, say, with, oh, I don't know, sulfate. We started with sulfate for this third equation. Okay? We might find that when we go through and balance, we get to our final answer much quicker than we did if we started with the barium. How would you know that? You already tried it both ways and saw that one way was easier than the other. So you still get to the final answer.
Yeah, no, I'm talking about the last one that you said that it was already balanced.
Yeah.
We don't have, yeah.
I didn't actually check it. Yeah. So if we go through and look at that real quickly, how many carbons on both sides? 1 and 1. Did you just say 2? The 2 only applies to directly what's in front of it. What's directly in front of it? The oxygen. If I put in parentheses, then the 2 can apply. There are no parentheses. It will not apply. Okay? More questions? Yeah.
Say save hydrogen and oxygen for last.
Yes.
Is there one that you say for very last? Oxygen or hydrogen?
Which one is it? I think it's oxygen. Or is it hydrogen? I don't remember. Which one do you say for very last with the electrochem?
I usually do oxygen last.
Do oxygen last? Yeah. You have to get to that section of the material. It's in 152 typically. Hi. Oh, yeah, I forgot. There was a quiz. It's a real classifying chemical reactions. Okay? So we just went through and came up with general ideas on how to balance a reaction. But one of our primary issues, or one of the very first rules on that list, was being able to predict the products. Well, if you don't know what type of reaction it is, you can't predict the products because you don't know what occurred. Okay? So there's certain classifications behind our reaction. Okay? You are responsible for recognizing an equation and saying it is one of these, was it 5? 5 types of reactions. Okay? Which is convenient. There are 5 multiple choice answers. Okay? So you will be given an equation and asked what type of reaction it is. Okay? So let's look at these equations and try and come up with an idea of what's happening within them. Combination reaction. What does combination mean? I knew I was going to get that answer. To combine or bring together. We're adding things to each other. Look at the overall results for a combination reaction. We started with how many species? 2. We got the plus sign dividing them. And we end with how many species? Only 1. There's no plus sign. Okay, nice and simple. Decomposition means we decompose something. It breaks it apart. So if we take a look at our overall reaction, we start with 1 thing and we turn into 2. Okay, does it have to be 2? Nope, it could be 3, 4, 5. Most typically it's 2. Same deal with the combination. Typically we'll combine 2 things together to make 1, but we could combine 3 things. Single replacement reactions. Okay? These get a little bit trickier, or now that we move into the single replacement, double replacement, and neutralizations, those get a little bit trickier to work with and predict. Okay? I'm trying to color code. Blue is our positively charged species, or can be a positively charged species. Red is our negatively charged species, or can be our negatively charged species. These single replacement reactions will most typically follow this format, okay, where you are substituting or sliding A in and exchanging it for B. Okay. Turns out that we aren't really looking at a cation, we're looking at a metal in that circumstance. But what charge does metals typically take? positive charge. They're typically our cations anyway. Okay? Double replacement reactions. What's happening in the double replacement? What does A end up with at the end? D. So A replaced C. Where did C end up? With B. So C replaced A. We have two replacements, hence double replacement. Last one, neutralization reactions. Take a real close look at the neutralizations. Can the neutralizations be classified as something else? Combination would mean we started with 2 and ended with 1. How many things do we end with? 2. So it's not a combination. It's a double replacement reaction. Okay? Why do we look at our neutralization reactions as a separate category from our double replacements? As a big hint, if we were going to add our phases into this, AQ would need to get written next to HA. It's an acid-base reaction. Acid-base reactions are one of the most common reactions. They are studied worldwide for general chemistry. Pretty much everything you go through and do in general chemistry is a neutralization reaction. Okay, we start with a reactive acid and a reactive base, and what do? We neutralize them. So in the process of mixing them, I end up with what species? Don't tell me HOH. I can also not really accept. I'm glad that didn't get recorded. H2O, also known as water. So we start with something really dangerous and we end with something not so much. It's a really good idea for an undergraduate lab. Okay? Everybody's going to be taking chemistry, so let's give everybody something really ridiculously dangerous, but then also give them the antidote at the exact same time. Okay? Works really, really well as far as chemistry goes. Okay? So pretty much all of your reactions fall under that neutralization reaction. Okay? So you are responsible for looking at these, identifying them, and to a certain extent, for some of them, predicting the products. Okay? As we go through, we'll probably talk about some extra types of reactions that you can run into as well that fall under separate categories. So, combination reaction. Okay? Typically referred to, or another way to refer to it, is a synthesis reaction, because we combine two things to make one new awesome thing. Okay, so we synthesize something. Okay, so there's 3 different types of reactions within a combination reaction. You get the reaction of a metal with oxygen, you get the reaction of a nonmetal with oxygen, and the reaction of a metal and a nonmetal. Okay? Seems a bit redundant because the reaction of a metal and a nonmetal is awfully similar to rule number 1, because oxygen is a nonmetal. Why do we subcategorize or pull oxygen out as a special reagent? It happens pretty much everywhere in our lives. We've got oxygen everywhere. So it's a very common reaction to look at. Most metals are not found in their elemental state. They are found in a state with reacted oxygen. Okay? So, here's a little question for you. Magnesium metal reacts of oxygen with oxygen gas to produce what? Okay, so what we want to do is now come up with an equation. How would we start our equation? Convert the names into our symbols or formulas. What is the symbol or formula for magnesium metal? Mg. Remember, when we write out our equations, also have to specify the phase. What is the phase for magnesium metal? It's a solid. Plus oxygen gas. What is our symbol for oxygen gas? Have no fear of ice cold beer. Our oxygen is diatomic. What phase? Gas. To produce, there's our reaction. Uh-oh, guess what you got to do with the combination reactions? you need to be able to predict the products. Okay? What is our product in this case? It's magnesium oxide. So it's the magnesium combined with oxygen. How many magnesiums, how many oxygens are required to make that compound? Okay. So I know what you all are doing, because I'm hearing 1 magnesium and 2 oxygens. To do that, where did that 2 come from? Most people are probably pulling from O2. We started with O2, right? We just combine it. You have to balance the formula. So now I don't care about the reaction. I need to balance the formula of magnesium and oxygen to make sure that they are in the proper ratio. What does that mean? We don't need to worry about parentheses, but we do need to worry about charges. What's the charge on magnesium? How do you know it's +2? You either memorize it or it's in column 2. What's the charge on oxygen? -2. How did you know that? You memorize it or you look at oxygen. It's in 2 away from neon. Okay, so it's a -2. Do those charges balance? Yes. What's the formula for magnesium oxide?
2 magnesium.
MgO. The +2 and the -2 canceled. Our formula is balanced as MgO. Okay. One thing I won't ask you to do is to predict the phase on this product. Okay, so you don't need to stress about that. Questions about that process for balancing the formula? Yes?
So since oxygen is on the gaseous state and is O2, so we're not counting that it has 2 oxygen, and we forget about...
When we go through to balance the formula, the only thing I am looking at is magnesium and oxygen. I don't care where the magnesium came from. I don't care where the oxygen came from. I look at my overall reaction. For a combination reaction, I combine these 2 elements. You'll notice in my general formula, I haven't specified how many of each of those elements or what those formulas are. That's because it's irrelevant in predicting the product. Okay? We just combine them, and then once they're combined, we now have to go through and make sure our formula is balanced.
So if it wasn't balanced...
If it wasn't balanced, then we can change our subscripts to make sure it's balanced. Once we have the balanced formula, then we can answer the next question, which is the equation balanced? But before we do that, or is that what you're asking? Is there another question there? No. Okay, so now that our formula is correct, we have to balance the equation. How do we balance the equation? Start with the magnesium. How many magnesiums do we have on each side? 1 and 1. That looks pretty good. How many oxygens do we have? 2 and 1. That's not balanced. What do we need to do? We need to make 2 magnesiums. How do we do that? We now change the coefficient. Now we can change the number in front. Okay? Now what do we do? Check it again. How many magnesiums do we have on the reactant side? 1, product side. 2, uh-oh, doesn't balance. What do we need to do? Put a 2 over there. Magnesium's balanced. Is our oxygen balanced?
Yeah.
Yeah. What do we do? Check it. What do you do? Check it. What happens if in this process you guess the wrong formula? Your answer becomes wrong. So you must check the formula before you try and balance the equation. This one is particularly obnoxious because if you go through and write the wrong formula, it looks balanced right away and you come up with that answer. Okay? Even if you go through and check, it still checks out because you used the wrong formula. Okay? Certain circumstances, if you use the wrong formula, you get really lucky because what happens when you try and balance it? It never balances. If you're getting in a situation where your equation is not balancing and you've checked it and changed numbers every single time you've gone through and checked, okay, that more than likely means your formula is wrong. Go back, ignore everything else, look just at the formula you wrote and say, is this a neutral compound? If it does, or if it is neutral, then what do? Move to the other product, if there is another one, and you check it. Okay? If both of them check out, erase all of your work on balancing and try again. Still doesn't balance, you should really find some help. Okay? Because there are problems that could potentially still run you into that issue. We want to do another one?
Sure.
Sulfur solid reacts with oxygen gas to produce sulfur dioxide, which, if I'm going to be nice, which might as well, is a gas. So, sulfur solid, S, solid, plus oxygen gas, which is diatomic, goes through to produce sulfur dioxide. How do I know there's two oxygens? Because I gave you the product. Why did I give you the product? What is the charge on the sulfur? What's the charge on the oxygen? If we add that up, what's the charge on our sulfur dioxide? Careful, there's two oxygens. -6. That's not neutral. You're right. Sulfur is not -2. What type of bond is there between sulfur and oxygen? Covalent. Do I care about the charge in a covalent bond? No. Okay? When we're looking at the covalent bonds, you are not expected to predict those from a reaction. We will tell you what your product is. That is why we know there's two oxygens. Because if we look at the name, what does it say? Dioxide, meaning death to two oxygens. Okay? Some people laughed, as long as I get one. Okay? Is our equation balanced? How many sulfurs do we have? 1 and 1. How many oxygens? 2 and 2. Our equation is balanced. Right? There's one more example on there. I'll leave it up here so you can write it down real quickly. But then we're definitely done with class. It is on the slides. It's just buried, I think, so you won't be able to see it. And we will